上的应用。
Okay, because the coat I may take off. Okay? Something wrong? Oh, and this one also needs to go. Okay.
Okay, thank you.
Hello? Yes, okay.
Well, good evening, everyone. It is my great honor to introduce Professor Peres from BIMSA. Professor Peres is a world-renowned mathematician who has made great contributions to almost all important areas of the probability theory. He is a member of the U.S. National Academy of Science. In this section, Professor Peres will talk about some highlights from the history of probability and local.
Good evening. It's a real pleasure and honor to be here, and I thank Professor Yao for this invitation. I want to thank my student Zitong Tian and postdoc Yun Li, who helped me prepare these slides. We've worked several days, and I hope you'll enjoy it. I would appreciate if you would start by closing your laptops, and then if I bore you, you can open them again. But at this point, please, everyone, close the laptops, okay? I still see some laptops open. Please close them so I feel like I'm talking to you and not to the back of the laptops. Okay, right there. Thank you. I appreciate that. So, so I want to take you through a tour of the last 115 years of probability, but they start even before that, where there was probability was done by the Bernoullis in the 1800s, but it was always either discrete calculations or non-rigorous. So Hilbert in 1900, in his famous list of questions, you in the red shirt. Hi. Can you close your laptop? I want, I'm prepared. Please close the laptops. I still see open laptops. Please close the laptops. The black laptop over there. Thank you. All right. So Hilbert asked to make mechanics and probability, which have a lot of math content, he asked to make them rigorous, precise. And it took a while before this was answered, but not so long. So here is a turning point in probability, which is this paper of Émile Borel in 1909, where he stated an asymptotic statement in probability. And Borel was the thesis advisor of Henri Lebesgue, who developed the measure theory, first on the real line, then on the Euclidean space, and he contributed to that. But he also stated this important theorem, so let's say what it says. So if you take a number in the unit interval, we know we can write it in a base B expansion. We're most familiar with decimal expansion. So let's think of decimal expansion. And in the decimal expansion of a number x, we can count how many sevens occur in the first n digits. And the number of sevens in the first n digits should be about n over 10, because we have 10 possible digits. So more generally, if we're working in base B and we're looking for some digit d between 0 and b minus 1, the number of k's so that the digit will occur, the digit d will occur, should, when we divide it by n, converge to 1 over b, 1 over the base. But the statement here is very strong because the statement says that the probability that this will fail is 0. So with probability 1, so it doesn't mean it has to work for every number, but it means that the numbers where it doesn't work have probability 0. Now what does probability 0 mean in the unit interval? Because it's an uncountable set. So probability 0 really means Lebesgue measure 0. And Borel, Lebesgue were kind of the first to realize this. Now, Borel defined this notion of a simply normal number, and he proved this theorem that almost every number is normal. So a number is normal means that it's simply normal, not just to base b, but to all the powers of b. So if we want a number to be really normal to base 10, then also when we look at, we want it to be simply normal to base 100, to base 1,000. So also if we look at triples of digits, like the frequency that 0, 0, 0 will occur, should go to 1 over 1,000, and even if we look at it only in locations that are multiples of 3, the frequency should be what we expect it to be. And it seems only fair that every digit will occur with its right frequency. But it's not so easy to write down a number where all the digits occur with the right frequency. And the first time this was done was actually in 1933. An undergraduate like you, like most of you, Champernoun, in 1933, so much later, he wrote down the first explicit example of a number which is normal to base 10. How do you get this number? You write 0, and then you write all the digits 1, 2, 3, 4, 5. Just you write the numbers. When you get to 10, you just write 1, 0, 1, 1, and so on, and you get a decimal expansion. And this number that you get just by writing all the integers one after the other as the expansion of a number in 0, 1, this number turns out to be normal. So if you look in here, you can pretty easily see the frequency of the digit 7 will be 1/10, and the frequency of 75 will be 1 over 100, and so on. So this is not so hard. But Borel's theorem, it gives us both less and more. So Borel didn't give any explicit number. He just said almost all numbers are normal. So that looks weaker than Champernoun. However, in some sense it's stronger. It says that Champernoun writes one number and Borel says almost all numbers are like this. But the strength of saying almost all is that we know that a union of events of measure 0 still has measure 0. So a union, as long as it's a countable union, finite or countable union, it still has measure 0. So what this means is that with probability 1, or with measure 1, almost all numbers x in the unit interval are simultaneously normal in all integer bases. 2, 3, 5, 7, all of them at once. The set of numbers that are not normal even in one base has measure 0. So the set of numbers that are normal simultaneously in all bases has measure 1. And this happened 115 years ago, and still no one can write down a number that's normal simultaneously in base 2 and base 3. We know there are lots of them. Most of them are like that. Avi Wigderson, who just got the Turing Award and earlier got the Abel Prize, described this as a problem of finding hay in a haystack. We know it's traditionally hard to find a needle in a haystack, but here, with these numbers, we have trouble finding hay in a haystack. We know almost all numbers are normal, both to base 2, both to base 3, both to base 5. We can't write down explicitly even one of them. And in particular, we suspect that a lot of numbers we know are like that. So pi, e, root 2, most mathematicians who thought about it believe that these numbers should be normal to all bases. But we can't prove they're normal even to a single base. So this shows our lack of knowledge, but also shows the power of the probabilistic method. With probabilistic considerations, we can get quite easily things that we cannot get constructively. Now, despite the fact that Borel was a pioneer of measure theory, his proof was not completely rigorous, and this was fixed a few years later by Hausdorff, who in 1914 proved Borel's strong law by proving a theorem about random variables that are bounded. So if we look, for instance, in how do we get a random variable that is bounded, we can, and has mean 0, we can just, for every number, look at the nth digit and put a 1 if the nth digit is 7 and 0 otherwise. So that would be a random variable that has mean or expectation 1 over 10, because for every digit, the measure of the points that have that digit 7 is 1/10. So, and all these variables, looking at different digits, they define independent variables. So Hausdorff proved Borel's law in this more general setting. If you add up bounded random variables that are all independent, they all have the same distribution, then the average will go to the expectation. So in this case, 1/10, and the same will happen if you count pairs of digits and so on. So, and Hausdorff was a great mathematician in the early part of the century. He contributed to topology, to set theory, and as you can see, also to the initial steps of probability. So he interpreted probability as measure theory, but the measure theory available at the time was only on the unit interval or in Rn, not the general measure theory that you learn today, that we learn today. And the proper setting of probability inside measure theory, where you can use any measure space, was done in a very important book by Andrei Kolmogorov, written in 1933 in Russia, where he gave a solid foundation to probability theory and really answered Hilbert's question from 1900. He also proved many important results, and I just have two of them here. So on the top we have an inequality. We have this same random walk we talked about, the sum of random variables, and the probability that the maximum of this random walk, or the maximum of the absolute value, will be bigger than lambda, has a bound. And this bound is variance of Sn divided by lambda squared. Those who have studied the first course in probability may recognize Chebyshev's inequality tells us that Chebyshev was a Russian mathematician from the 19th century. He proved the inequality, which is still very useful, which would tell us that the probability that just the last variable, Sn, is bigger than lambda, that probability will be bounded by the variance of Sn over lambda squared. And what Kolmogorov tells us is that he can get the same bound as Chebyshev for an event that's much bigger, that the probability that at any step along from 1 to n, the walk exceeded lambda. And this is the first example of something that we now call a maximal inequality. These were also discovered independently by Hardy and Littlewood in analysis. And later these streams of thought from analysis and probability merged together. But today, we know that the key to prove many limit theorems is to first understand a maximal theorem, and this is certainly the first one in probability. And he also used that theorem to get a strong law of large numbers under the optimal hypothesis. And that's one thing. Another thing we learn is that often it's important to get the limit theorem to understand what is really needed. So Borel and Hausdorff were working with bounded random variables, and Kolmogorov showed that the exact sharp condition for the average to go to the mean is just that the variables have a finite expectation. So the absolute value have a finite expectation, what we would call integrable functions in the Lebesgue sense, and in the sense that the limit condition will hold under that, and it will fail for any variable where the expectation is not finite. So these are just two of the theorems in his revolutionary book. So another influential Russian probabilist working around the same time, and they often collaborated, was Alexander Khinchin, and he looked at a question. So let's go back to a random walk that's more restricted. So even just plus minus 1, equally likely. So the first random walk we would consider where we add variables that are 1 with probability half and minus 1 with probability half. And then we can ask, so the law of large numbers tells us that when we add these variables and divide by n, it goes to 0. But we can ask, how big can the sum be? Can it be close to n? It's less than n, but what is the right order of magnitude? And Khinchin found the exact answer. So you can draw a curve, which is the square root of 2n log n, and the Brownian motion or random walk, I'm jumping ahead to tell you about Brownian motion, but the random walk will reach this curve asymptotically infinitely many times. So this is the statement about a lim sup Sn over root 2n log n will be 1. And by symmetry, it will also reach minus root 2n log n, because if I look at minus Sn, it's also a random walk. So the Brownian motion will reach both of these curves, but it won't reach higher. So it won't reach, the square root of 2.1 n log n. So root 2 n log n is a sharp result. And what is interesting in this result, it's kind of the first time that something so refined with a double log occurred. And it's not just the result, it's also the method of proof, because he needed to understand two things. One is to control what is the probability that the Sn is very large. And this was understood not just by him, also by Hardy and Littlewood, by Kolmogorov, by others. But the innovation that Khinchin did, he understood that I don't need to look at Sn at all times, because these are very correlated. I just look at them along a sequence that grows exponentially, like Sn when n is 2 to the k. I control the walk at those times, and then I can interpolate because these sums are very correlated with each other. And this understanding both of large deviations, what we call now concentration inequality, and of the right dependent structure is the foundation of a lot of sophisticated studies in modern probability, and it started with this proof of Khinchin's theorem. Khinchin assumed, I'm going forward, I'm trying to go backward. These buttons, I have to press the buttons correctly, sorry. So Khinchin's theorem was later generalized by Hartmann and Winter. All you need for this theorem is that the variables have mean 0 and variance 1, so you don't need them to be exactly these Bernoulli variables. And Paul Levy proved that the same thing holds for Brownian motion, which is the next player in our show. So around the same time that Khinchin was proving his theorem, in the United States, Norbert Wiener was formalizing an idea of Einstein. So Einstein and in physics and Bachelier in economics looked at how does a random walk look when you move far away. And for Einstein, this was a way to measure mass in physics. So they thought of the process of movement of atoms, and the name Brownian motion came from the observations of the botanist Brown much earlier. So all of this was very interesting physics, but it wasn't mathematically rigorous until Norbert Wiener found a way to construct Brownian motion as a random continuous curve, and he did it by using a random Fourier series. So you use random variables which are standard Gaussian or normal, and you combine them in a Fourier series. So it's a Fourier series with random coefficients. I'm not going to go into the details of why this works, but this turns out to be a random curve that nicely describes the limit of random walks as we look at them at a finer and finer scale. However, this Brownian motion, while you see a Fourier series, you might hope that this series gives you a nice smooth function, but two great harmonic analysts, Paley and Zygmunt, shortly thereafter proved that in fact the curves of Brownian motion are nowhere differentiable. So Weierstrass in the 19th century constructed explicit functions that are nowhere differentiable, but these were seen as exceptional functions, something very unusual. And what Paley and Zygmunt tell us is that, in fact, a typical random curve, the Brownian motion, is nowhere differentiable. So that gives a problem in doing calculus with these curves, which took some years before it was solved by Ito, and we'll come back to that. Now, another great figure in the study of Brownian motion after its construction by Wiener was Paul Levy in France, and he gave a more natural construction of Brownian motion. Instead of writing a random Fourier series, you take a random walk and you kind of refine it step by step. So I'm not going to go into details, I don't have time for that, but those interested, look up construction of Brownian motion, Levy's construction of Brownian motion. There are many books that cover it, and I'll spill a secret. I even myself, with Peter Morters, wrote a book of 500 pages on Brownian motion, and right at the beginning we have the construction of Paul Levy, and this book you can find the PDF freely on the internet, as there are many other sources that describe Paul Levy's construction. Now, Paul Levy did many other things, and another beautiful thing he did was found the connection between Brownian curves and analytic functions. Namely, if you apply an analytic function to a Brownian curve, then you get a new Brownian curve, but it may have a time change. So it may be sped up or slowed down according to this, the derivative, or the square of the derivative of this analytic function. But it still means if I look at the curve of Brownian motion, at the path, ignoring the speed that I move on it, then the curve is conformally invariant. It's preserved under analytic functions, and from that a lot of corollaries flow, like harmonic measure, which is the way the hitting distribution of Brownian motion is preserved under conformal maps, and that's a crucial connection. As we'll see, Kakutani reached a similar conclusion from a different approach that led him to generalize it to higher dimensions. Another beautiful theorem of Paul Levy is not exactly probability, but it's a measure concentration result, which led to a lot of probability progress later. So look on the sphere, and look at the set on the sphere of half the surface area. Okay, so we know the surface area of the sphere in any dimension, but take a set A that has half the surface area. Now, for any such set, we can look at the epsilon neighborhood. So all points A epsilon are all points that are within epsilon of A. And we can ask which sets A minimize the area of the epsilon neighborhood. And the answer he found is, maybe it's not surprising, it's just hard to prove. The answer is that you should take A to be the half sphere. Now, this is a natural result. It's analogous to the fact we know in the plane of all sets of equal area, the one with the smallest perimeter is a disk. But proving it on the sphere has an important consequence in high dimensions, because what you find is if you take a sphere in high dimensions, so think of an n-dimensional sphere where n is very large, and we take a half sphere. So a half sphere, has half the measure, and we take an epsilon neighborhood of it. So epsilon could be 1/1,000,000, but it's fixed. Then it turns out that by taking the epsilon neighborhood of half sphere, we're covering almost all the sphere. So the part that's not in A epsilon has surface area which is exponentially small in the dimension. This is a high dimensional phenomenon, and it is kind of an important example of concentration of measure in high dimensions that is a key tool later in probability, and even today in combinatorics and machine learning in many areas. Now, on the sphere, for the half sphere, you can see this concentration just by simple geometry. But what Paul Levy tells you is what you find for the half sphere then applies for any set of measure 1/2. So if you take any set of measure 1/2 on the sphere, look at the little neighborhood of it, this will already capture almost all the sphere in high dimensions. Now, today I mostly will tell you stories of great mathematicians and their discoveries, I want to show you one proof. And this will be Lindbergh's proof of the central limit theorem from 1922. So many of you have, I think, probably all of you have seen the central limit theorem, maybe under a different name, normal approximation, Gaussian approximation, but I think probably most of you have not seen this proof, which is really spectacular beauty, and again has inspired much later work. So what does the central limit theorem say? It says that if we have variables, they have to be mean zero, and they have to have finite variance, and let's just normalize that to be variance 1. Let's say they all have the same distribution. So it's the same random walk we looked at before. We add them up. Here I'm assuming something which with more sophistication can be removed. I'm assuming that the third moment is finite, so expectation of xi cubed is finite. Then when you add these variables, remember Khinchin told us that in the lim sup, in the worst case, they will grow like root 2n log n. But the central limit theorem asks how they, not what they do in the worst case, but what do they do typically? So the typical answer is if you take these n variables, divide by root n, the distribution you get, so the probability you fall in some interval, is converging to the probability that the standard normal variable with density 1 over root 2 pi e to the minus x squared over 2, the standard normal variable, falls in that interval. And the first proof of any central limit theorem, very special case by De Moivre, more than 200 years ago, used explicit calculation and Stirling formula. There are lots of later proofs, sophisticated proofs that use Fourier transforms, but Lindbergh's proof stands out in that it's both general and elementary. So I want to show you this proof. So the key behind Lindbergh's proof, the reason central limit theorem holds at all, is some fixed point property or stability property of the Gaussian distribution. If I take a normal variable, say a variance 1, I add another normal variable, also a variance 1, then it's just an easy calculation that the sum will itself be a normal variable, its variance will be 2. So the variances of independent variables add, but the Gaussian has the property that when we add 2 of them, we get another Gaussian variable. Now, Gaussian variable of variance 2 can be obtained, or normal Gaussian, these are synonyms, can be obtained by 1 of variance 1 just by scaling by root 2. So this is a stability property. Similarly, if I add n independent normals, this is also normal, but with variance n. So if I add n independent normals and divide by root n, this will just have the original normal distribution the same as all the summands. So that's some kind of stability or fixed point property of the normal distribution, and we want to go from that to the central limit theorem. So central limit theorem would say that the probability that this average will lie in some interval, it's not an average, it's a sum divided by root n, probability that this ratio will lie in some interval will be asymptotically the same as the probability for a normal variable, but instead of asking that it lie in an interval, which is like applying an indicator function to this ratio, I can apply some other function, and convergence in distribution is the same as saying if I have continuous functions of bounded support, the expectation of f of this ratio should be close to expectation f of a normal. But here I wrote a normal already in a way which I want to use. So remember that if I take n standard normals independent, add them up and divide by root n, this ratio itself will just be a standard normal. So here I could just write z1 for what I want to prove, but z1 has the same distribution as this ratio. So I'm writing it in this form. It's enough to show for the central limit theorem that this ratio goes to 0. I'm sorry, this difference goes to 0. Difference of expectation of f applied to this ratio and expectation of f applied to the other ratio. So there are two ideas to do this. One is by approximation, all continuous functions are close in L1 to smooth functions. So it's enough to prove this for smooth functions, and what Lindbergh needs are functions with a bounded third derivative. And And then his idea is he looks at these two differences and says, well, I want to replace all the x's by the z's. How about I do this one by one? So replace x1 by z1, x2 by z2, and so on. And let's see what is the change in the expectation when we do this replacement. So again, this is really the only proof you'll see today. So, and the proof just takes this one page. So hang with me. So we're going to do one replacement. So this is the kth stage of the replacement. We have y is the sum of all the x's, but with the first k minus 1 x's. And then we skip xk and we add the last n minus k z's. Okay, so what we want in the replacement is to compare f of y plus xk, because that will be the sum of the first k x's and then z's, to y plus zk. That will be the result when we replace one xk by zk, right? We want to show these are close. So we do it using Taylor expansion. So remember, we assume that f is 3 times differentiable, third derivative is bounded. So we all learned Taylor expansion. Second order Taylor expansion with remainder. What does it tell us? That we can write this as f of y plus a first derivative term, a second derivative term, and an error. Now but we're looking at a difference. So the f of y term cancels right off. The linear term will give us, when we expand the first term there, it will give us an xk over root n f prime of y. And when we do the same thing on the right-hand side, we'll get zk over root n f prime of y. So we bunch these together. So the contribution of the linear term will be xk minus zk over root n f prime of y. And similarly for the quadratic term, in the Taylor expansion, we get xk squared minus zk squared over 2n f double prime of y. And then there's the third order term, which is an error term, which is of order of the third power. So here the third power will give us xk cubed and zk cubed and n to the 3/2. And the big O means it's up to some constant that we don't care about. So all of this was inside the expectation. Now we take the expectation of all that, and we have already matched the expectation of xk and zk, so that those expectations are both 0, so they just give us 0. And then we've also matched that xk squared and zk squared also have the same expectation, because these variables have variance 1. So when we move the expectation inside, the second term will also vanish. So all we're left with is the third term, and here we assume that xk cubed has a bounded xk cubed has a bounded expectation. For zk cubed, there's nothing to assume. A standard normal cubed, we can calculate its expectation. It's some finite number. So overall, we get that all of this is of the order n to the minus 3/2. And this is the effect of switching one x to another z, just using Taylor expansion. And now we just do this n time, and we accumulate all these errors. And in the worst case, we get an error of n to the minus 1/2, which turns out to be the right order of magnitude in the central limit theorem. So central limit theorem tells us that we have approach to the normal distribution. We can ask, how close are we? And the answer is, we're 1 over root n close, at least if the variables have a third moment, which is what we assumed here. So that's the whole proof of a central limit theorem. And this idea of replacing one by one, sometimes called the delta method or the Lindbergh method, it was considered, this is an ancient proof. We have more modern proofs. In the 1970s, there's a probability book that describes this. I loved this proof when I read it in Bryman's book from 1968. But then Bryman wrote, well, this is an old proof. Now we have more modern methods. But in fact, in the 2000s, the ideas of this proof had a resurgence, and they're now used all over the place. Okay, so we move on from Lindbergh, and I want to tell you about George Polya. He was a mathematician primarily working on inequalities, complex analysis, but he also made a crucial contribution to probability, and this contribution came about for a funny reason, he was walking in the garden in Vienna, next to his office, and his colleague, who just had a new fiancée, was also walking in the garden with his fiancée. So Polya was walking kind of randomly, not paying attention, but he kept bumping into his colleague and the fiancée. And he got worried maybe the colleague would think that Polya is following him and trying kind of to snoop what he's doing. And he knew he wasn't doing it. So he thought, the fact that I'm meeting this colleague again and again, is this surprising or is this to be expected? And being a mathematician, he abstracted the question to a question about an infinite lattice. So suppose you have Z2, which is just a product of the integers with itself, and we do a random walk in Z2. So from every vertex, we walk to one of the 4 neighbors in the lattice. And now, instead of asking about the problem of collisions, because in the lattice, the problem of 2 random walks colliding, we can look at the difference of the 2 walks and ask about that difference returning to 0. So, because he was abstracted the question to lattices, not general graphs, Polya studied the question of returning of a random walk to 0, which we call recurrence. So a random walk, or more generally a Markov chain, is recurrent if it returns infinitely many times with probability 1 to its starting point. And what Polya proved by a nice calculation is that in 2 dimensions, so a random walk which is symmetric goes to all the neighbors equally likely. In 2 dimensions, a random walk in 1 and 2, 1 dimension is really easy. In 1 dimension, I walk left, I walk right, of course I will return to the starting point. In 2 dimensions, it's not obvious, but Polya proved it, that in 2 dimensions, I will return infinitely often to the starting point, and the same doesn't hold in higher dimensions. So in 3 and higher, a random walk starting at the origin might never return to the origin. If it does return, of course it could return, but it will definitely only return finitely many times, and typically a small number of times. So later, Kakutani, who will soon see some of his exploits, described Polya's theorem by the description that a drunk man, right? We think of a drunk man is doing a random walk because he doesn't look where he's going, but he will still find his way home because he's walking in 2 dimensions. But a drunk bird will get lost forever. So that's kind of Kakutani's slogan. Now, I'm going to jump ahead like 85 years to tell you of my own interest in Polya's story, because in 2004, I had a student, Manju Krishnapur, and we looked at Polya's original motivation. So his original motivation wasn't about returning of a walk, it was about collisions of 2 walks. Since he was looking at the lattice, the problems are really equivalent because you can subtract. But if you look at other graphs, the problems are different. And here's an interesting fact we found. So there are graphs, and this is the simplest one, the comb lattice. So here you see a finite piece of the comb lattice, but really think of this going infinitely far horizontally and vertically. So the graph is a subgraph of the 2-dimensional lattice. You take the x-axis, the whole infinite x-axis. Together there's all the lines parallel to the y-axis. So this is the graph we're walking on. And we do simple random walk on this graph, meaning we start at some vertex and we walk uniformly to one of the neighbors at every step. And then this graph is still recurrent. In fact, a beautiful theorem is that if you have any recurrent graph where the random walk will return and you take a subgraph, that is also recurrent. It's the theorem of Nash-Williams. But here, I'm not asking any more about recurrence. This graph is certainly recurrent. I'm asking about 2 independent walks, walking on this graph. Are they going to meet infinitely often? And by meet, I mean I want them to collide, so to be in the same place at the same time. Will these walks meet infinitely often or not? And the answer on this graph is they won't. So even though each of these walks will return to the origin infinitely often, they will do this at different times, and after a finite time, they will never meet. So in this graph, although a walk returns to the origin infinitely often, 2 independent walks will not. So this is kind of, this graph doesn't have the infinite collision property, and studying the infinite collision property, after this paper there were a bunch of others, some by me, some by other people, where the collision property was studied, and it turns out to be more delicate, harder to study than recurrence. Okay, so this was just a jump ahead in our chronological story, and Kakutani, who told us, who had this whimsical description of the bird, he is one of the important probabilists of the century, and he found a crucial connection of Brownian motion, so this object that Wiener constructed, to potential theory and harmonic functions. Now, when Wiener constructed Brownian motion, he was really thinking of Brownian motion in one dimension. But once you have Brownian motion in one dimension, you can easily construct Brownian motion in multiple dimensions. Just make the x-coordinate is one Brownian motion, the y-coordinate is another Brownian motion, and you have a Brownian motion path multidimensional. And so you can look at two-dimensional walk or higher dimensional walk, and for simplicity, let's look at, so Kakutani studied them all, but let's look at dimension greater or equal 3. Why is this turning off? Am I doing something wrong? So let's look at dimension greater or equal 3, and the advantages in dimension greater or equal 3, the Brownian motion, just like the random walk, is transient, so it goes off to infinity eventually. But if I have a compact target, like a ball or a cube, and I start outside the target, I can ask, what's the probability that I will hit this target? And this probability, the observation of Kakutani, this observation is very easy, but what he did with it is remarkable. The observation is that the probability that I hit the target is a harmonic function of the starting point. Now, what's a harmonic function? One definition of harmonic function is its value at a point equals the average of its values on any little sphere around the point. And the fact that Brownian motion is isotropic, it goes equally likely in all directions, easily gives us this harmonic function property. But then he went further and proved there's an equivalence. So for a long time, people in analysis were studying, if I have a compact set K, when is it large enough so that there exist harmonic functions on the complement of K, which are bounded but not constant. So this is related to electrostatics, and this is such a set K is called positive capacity. And so this was studied, with physical motivation analytically, and Kakutani showed this is completely equivalent to a probabilistic question. So that analytic question about harmonic functions is equivalent to a question of, does Brownian motion hit the set? So this is just one of Kakutani's many, many results. I'll tell you one more in a minute, but I want to mention an important meeting so Kakutani was in the US in the 1930s and early 40s, or until about 1941, and then after Pearl Harbor, when Japan and the US were in war, he managed to get on the last civilian ship back from US to Japan, and he was constantly worried that one side or another will sink the ship. And he was very productive at this time. He kept proving new theorems, and he was worried that if the ship is sunk, all these theorems will be lost. So he kept writing these theorems in 2 copies. One he kept for himself, the other he put in bottles and threw over the side of the boat. Anyway, luckily he did get to Japan, and in Japan, there were mathematicians during the war. Japan didn't really see their value, so they were just left to their own devices. So Kakutani met with 2 other Japanese mathematicians, Yoshida and Ito, and they all decided to study Brownian motion. They thought they would study it together, but they went and studied it in different directions, each on its own. Now, each on his own. Let me just verify, do we usually have a break here, or what is the convention about these talks? So, and when do we're supposed to end at 9 or before, or what's the?
If you like, you can take a 5-minute break. If you want to continue, it's okay.
Okay, so for now I'll continue. Maybe we'll take a break a bit later. And so I want to tell you, but why is this turning off? Okay, I want to tell you one more theorem of Kakutani that he proved together with Dvoretsky and Erdos, because it has a nice story with it. So they were looking at the path of Brownian motion. Now, it's easy to see this path has local maxima. So there are points that are maxima both to the left and to the right. Even the global maximum exists. But they were asking, is there a point of increase? So point of increase is a point which is so this would be a point of increase. It's a point that's a maximum to the left and a minimum to the right. So this is a point of increase of the Brownian motion. Say we run the Brownian motion for a unit time. Is there a point of increase? So this was a very delicate question, and they worked all day and several days, and then they thought they had a proof that there is a point of increase. Now, Kakutani, by the way, told me this story personally. I was a postdoc at Yale University in 1991, and Kakutani was retired but still there, so I heard this story directly from him. So they thought they had a proof that there is a point of increase, and then Kakutani, Dvoretsky and Erdos were both staying in New York City, in Dvoretsky's apartment, and Kakutani went down to his car to drive to Yale University where he was working. So it's like an hour and a half away. So he goes down to his car, tries to turn the car on. It won't start. He tries 15 minutes, won't start. So he goes back to Dvoretsky's apartment, explains the situation, and gets permission to stay there until the next morning when he can call the mechanic. So as they're getting ready for bed, they're discussing the fine points of their proof, and they see there were some gaps. Some points in the proof were not right. They correct them, but then new gaps appear. Anyway, by 2 a.m., they had proved the opposite of what they initially thought. They actually proved there are no points of increase. So that's the true theorem. There are no points of increase. So Brownian motion, although there are points that are maxima to the left and the right, there's no point. With probability 1, there's no point at all which is a maximum to the left and a minimum to the right. And so they proved that, and then finally went to sleep. The next morning, when Kakutani went back to his car, before calling the mechanic, he decided he would try once again just to start the car, and it started right away, no problem. So Kakutani conjectures, in some sense, the car knew that something was wrong with the first proof. This theorem of non-increase has intrigued many probabilists later, and there are at least, the original proof is quite complicated. There are at least three simpler proofs found later, one of them by Adelman, one by Birdsey, one by me. So I'm attached to this story because I have a personal connection. Okay, here's a picture from Yale, 1991. This was a conference in honor of this mathematician, Roy Adler, who was a student of Kakutani. And Kakutani is right next to him on the left. So that's Kakutani in 1991. And anyone sees me in this picture? I was also there, looking a bit different on the other corner. This is 91. I was a postdoc at Yale, and I really benefited from many discussions with Kakutani, both about math, about history, about life. He was really a remarkable man. Now, the other Japanese mathematician that Kakutani met had perhaps an even greater impact on probability. That's Kiyoshi Ito, who overcame the problem, how do you do calculus with Brownian motion? So he defined the notion of a stochastic integral. So it looks like a Riemann integral, but I have to be more careful and what kind of convergence you have. So, and one sign that something is different from what we're used to is in how this stochastic integral behaves. So this is an example of what's known as Ito's lemma or Ito's formula. So we're used to, if we compare f at 2 points, it should be the integral of f prime. But here there is a stochastic integral. It's not the usual integral because the function is not differentiable. So you cannot have a usual differential. But there is this meaning to this formula. But you have to have a second correction term. So f has to be twice differentiable. And this is Ito's formula is kind of the foundation of a whole field of stochastic analysis. Stochastic PDE are an active field of probability, especially in China. So China is one of the centers of this field. I'm not going to talk much about this field. And I want to jump to another law of the iterated logarithm proved in 1947. So Kai-Lai Chung was the greatest Chinese probabilist of the 20th century. And he, in 1947, he finished a thesis at Princeton. And he proved another law of the iterated logarithm, kind of a counterpart of Khinchin's. Khinchin's was in 1920s. Chung was in 1947. So he looked at something more subtle. So you look at the random walk. So Sn is still, Sk is still a random walk like before. So think of adding plus minus ones. It's more general, but you get the idea just by adding plus minus ones. And now you look at the random walk until time n. And but you look at how far the random walk has traveled. So Sn star is the maximum of the absolute value of the walk until time n. So this tends to be large. Typically, it's at least of order root n. But he asked, how does it behave when it's smallest? So on the rare times when it's smallest. So what does it mean when Sn star is small? It means that the random walk until this time has stayed kind of below what it's supposed to be, below the root n. And just like in Khinchin's law, we look at when the random walk is above where it's usually, above the root n. Here we look when the random walk is below root n, but not just at one time. We want it to be below this root n throughout the past. And then there is, so how far below root n will it be? Well, it's the same log n from Khinchin. And the constant that comes is pi over root 8. Now, why pi? Well, Chung understands, and we now understand even better, this is related to the fact that the eigenvalue of the Laplacian on a unit interval is pi squared over 8. So again, this theorem is interesting not just in the result, but the method of proof was the basis of a lot of later work. So this is again a dramatic result. Chung also proved the ultimate recurrence theorem in one dimension. So in one dimension, we said it's very easy to show that simple random walk is recurrent. But if you have random walk with long jumps, it might never return to the origin. It might jump back and forth. So Chung and Fuchs found the exact condition for a random walk in one dimension to return. And Chung also wrote several influential books that trained generations of probabilists all over the world. One of my favorites is his last book, Green, Brown, and Probability, that discusses the connection of the green functions, Brownian motion, through probability. But he had a bunch of earlier books too. And I'm going to jump to another important probabilist, Joe Doob. American, worked in University of Illinois basically all his life. And his greatest contribution was developing the notion of martingale. This notion had its roots in earlier work, especially by French mathematicians, Paul Levy, who we saw before, and Jeanville. But really, Doob's work showed the full power of this concept. So a martingale is a generalization of a random walk. Instead of adding independent variables, a martingale has the property that the expectation at every step, so if I take the expectation at every step and condition on the past, so here is the expectation at time n plus 1, but given the whole past, so I'll write m1 up to mn, you can condition on a sigma field, and that would be more complete, but let's just do expectation of mn plus 1 given m1 to mn equals mn. So this property would hold for a random walk if I'm adding variables of mean 0 that are independent. But this is much more general, and martingales can be manipulated much better, yet they seem to occupy a sweet spot where they occur all over the place, but they can be analyzed almost as well as sums of independent variables. So they're more flexible, occur more, yet can be analyzed in great detail. One of Doob's many theorems is that the maximum of, so he proved maximal inequalities for martingales. Here is one of them, his LP maximal inequality. So this, again, it kind of echoes Kolmogorov's before. So we take a martingale up to time n, and it even can be more generally a sub-martingale, but let's just think of a martingale, and we look at the maximum of the martingale until time n, and we look at the LP norm. Remember, what's the LP norm? I take this maximum, I take it to the pth power integrate, and then take pth root of that. And for all p bigger than 1, this maximum is not much bigger in LP than the last term. This is Doob's LP inequality, maximal inequality, again, extremely powerful result, certainly motivated by Kolmogorov's work much earlier, but goes beyond it. And this is just one theorem. He published a revolutionary book in 1953, Stochastic Processes, that again changed the nature of probability from then on. There's a story about Doob's book. At the same time he was writing it, William Feller, another important probabilist, was writing a different probability book, which was also very influential. And they knew each other, they admired each other, and they knew that both these books would be important. So they wanted to use the same terminology. But the problem is, one of them believed, Doob thought that they should call, functions on a probability space chance variables, and Feller thought they should be called random variable, and they argued and argued. They couldn't reach an agreement, but since they were both probabilists, they had a method to reach an agreement. They tossed a coin. Feller won, and that's why we talk these days about random variable. I think if the coin had gone the other way, all of us who talk about probability in English would be talking about chance variables. Because these books were so important, so influential, everyone adopted the terminology in these books. Before that, there was split. Some people did this, some people did that. After these books came out in agreement, everyone just used the terminology in those books. I'm going ahead to another influential mathematician, Hillel Furstenberg, who also happened to be my thesis advisor. He did his thesis in Princeton with Bochner. And one of his innovations was to generalize this idea of connections of random walks and harmonic functions to general random walks on groups. So he constructed for any group a suitable boundary where the random walk will converge to that boundary, and that boundary will tell us all the information we need about harmonic functions on the group. So he called it the Poisson boundary. If he didn't give that name, if he just said a boundary, we would all be calling it the Furstenberg boundary. And indeed, many places it's called the Poisson-Furstenberg boundary. And so one related work he did was with Harry Kesten, another important probabilist, where they considered the rate of growth of a product of random matrices. So you take small matrices, they could even be 2 by 2, and you multiply them. And they asked, how fast does this product grow? So maybe I'll go back to the board. So now you take matrices, and here is a simple example if you want to think of it. Suppose that A1 is this matrix with probability 1/2. So each AI is, and this matrix with probability 1/2. The important thing is these two matrices, they don't commute. So I take these two matrices. This is just one example. This is a distribution on the space of matrices. And then I look at the product A1, A2, A3 times AN, and ask how fast does this grow? So you take any norm that you like on this. So a norm could be just sum all the elements of the matrix. You take the norm of this, and you ask how fast does this grow? So you could take the log of this and divide by n. And they showed that this limit exists. And it has, these days, it's called the Top-Lyapunov exponent because of related work of Lyapunov in dynamical systems, but this is really their discovery. Now, suppose these A's, instead of being matrices, they were just numbers. Then how does the product grow? How do we understand the growth of a product? We just take a logarithm that converts the product to a sum, and we're in the situation of a law of large numbers. So if we have independent one by one, independent random variables that are real valued and we multiply them, we can understand it using the law of large numbers just by taking a logarithm. The same thing applies if the matrices are diagonal and I multiply them, then all the action happens in each entry. So diagonal matrices we can also easily handle. And the same works if the matrices commute. If I have matrices that commute, I can diagonalize them simultaneously and everything is easy. Furstenberg and Kesten went beyond that and they looked at matrices that don't commute, and they showed that you still have the log of this product. When you divide by n, this still has a limit. And this is extremely important in dynamical systems, because if you take a dynamical system, which is a function on, say, a manifold, which you apply again and again, and you want to understand the effect of this dynamical system, well, how do you understand the effect? You take a derivative. Now, if you take a derivative and you apply the chain rule, then you'll see that the derivative is a product of the derivatives. The derivative of the iteration is a product of the derivative of the function itself along an orbit. So if you're in one dimension, you're in good shape. You can understand everything. If you're in higher dimension, the derivatives become differentials, and they basically become matrices, and you're into the situation that Furstenberg and Kesten studied. So their theorem, although it was proved in a setting of probability ergodic theory, it's become fundamental in dynamical systems. His main field was ergodic theory, and he opened a whole new field by connecting ergodic theory to combinatorics, but that gets us into beyond the area I'm describing today. We go to another important problem, and there are so many of these that I'll be able to give you just a little taste about what they did, but Varadhan is famous for multiple fundamental works on large deviations, so the probability that a random walk goes far from its mean. We have universality. If we look at a random walk with nice variables, say bounded, then the typical behavior of the sum is given by the central limit theorem. But if you ask not for typical behavior, but for outlandish behavior, unusual behavior. So this was started by Kramer in the 1920s to look, and by Bernstein in Russia, by Kramer in Sweden, but Varadhan, Struck refined this theory. It's called the theory of large deviations, where you understand the probabilities that a random walk behaves very unusually. So initially the motivation was actually insurance. You want to understand what's the chance of unusual events. Central limit theorem won't help you there. But Varadhan really took this kind of theory to new heights and applied it in various unexpected settings. He also went and looked back at the differential equations of math physics that had been there for hundreds of years, but he looked at them with a fresh probabilistic perspective, what's called hydrodynamic limits, where you try to understand, instead of what classical physicists did, they wrote down differential equations that describe a system, and then if this matched experiments, they were happy. But he tried to understand where these differential equations come from when you look at the microscopic movement of particles. And this is called the hydrodynamic limit theory. Usually he and his collaborators, students, were able to confirm that the physics equations were right, but sometimes they found correction terms which were not known in the physics literature. So again, this is just part of his contribution. He got the Abel Prize in 2007. It was. I'm again pressing the wrong button. Sorry about that. So next I want to tell you a bit about percolation, a topic that is important in modern probability, where in percolation we have a lattice, and every edge is open with probability P, closed with probability 1 minus P. So this is an example of percolation in the two-dimensional lattice with P equals 0.51. So it turns out that 1/2 is very special here, and here we're right above 1/2. So the basic question of percolation is to ask the connected components in this random graph. Are there big ones? If we do it in the whole lattice, is there an infinite connected component? So this process was investigated with several motivations. So Hammersley and Welsh in England looked at this while studying gas masks to understand how long will a gas mask prevent gas entering, how long will it protect the wearer. Erdős and Renyi studied percolation on a different kind of graph, the complete graph, where we have n vertices and all edges connect them. And these two theories started developing separately and then merged much later. Harry Kesten, a key probabilist of the 20th century, proved that the critical probability in 2 dimensions is 1/2. So what does that mean? So for every number P, I can ask, is there an infinite cluster? Is there an infinite connected component or not? And the answer turns out to be that in any dimension, 2 and higher, there is a critical number PC. Below it, all the clusters are finite. Above it, there's always a unique infinite cluster. Only in 2 dimensions, we know what's the exact number. It's 1/2. In 3 dimensions, we know it's some number less than 1/2. We can approximate it numerically, but we don't know the exact number. Kesten proved it's 1/2 in 2 dimensions, as people suspected, and he also proved that at the critical value, so if I take P equals PC, which turns out to be the most important thing, critical percolation turns out to be the right thing to study, the most fascinating thing, proved that there is no percolation, meaning all the clusters are finite. Now, this was in 1980 when he did this. In dimensions 3 and higher, it's still open whether there is an infinite cluster at PC. I say 3 and higher, the real ones that are completely open are 3, 4, 5. From dimension 11 on, there is a proof, basically due to Hara and Slade, that at PC there is no infinite cluster. So very high dimensions are behaving like a tree which we can understand. And it's believed that the technique with more computing power and would extend all the way down to dimension 6. But dimensions 3, 4, 5 require fundamentally new ideas and are really beyond the reach of current mathematics. Now I want to jump to percolation in the plane and tell you one of the most fascinating stories, maybe the most fascinating story of probability in my lifetime, which is the conformal invariance problem. So suppose we are in 2 dimensions, and there's a fine lattice that you don't even see here. Its mesh is so fine. So you do a square lattice, but with delta, edges of length delta, and you do this percolation inside some domain. Then I can ask, is there an open path? And I want to do just critical percolation, so P equals PC. Is there an open path that connects the left edge to the right edge? So the left red edge to the right red edge. So, and this path has to stay inside the domain D and be in this fine lattice. So the interesting question, which was raised by many physicists and prominently by Michael Eisenman, is, is this probability of connection in the limit as the mesh goes to 0, is it conformally invariant? So if I apply an analytic one-to-one map to this domain, will I get the same probability in the limit? So it wasn't even clear that the limit exists. It wasn't even clear that if the limit exists, that the rotation, that it will be preserved by rotation. But any conformal map locally, what it consists of is rotation and scaling. So can you combine rotations and scalings and get this probability not to depend on the domain? And a physicist from Oxford, Cardy, believed this conformal invariance is true and used remarkable but non-rigorous methods from physics, what's called Coulomb gas calculations, to give a formula for the probability. So if you have any simply connected domain, the Riemann mapping theorem tells you that you can map it to a disk, and let's assume that the boundary is locally connected so that the mapping extends continuously to the boundary, and then so you can take, if you believe in conformal invariance, you can just solve the problem in the disk. So in the unit disk, these 4 points, P1, P2, P3, P4, will be mapped to 4 points, Z1, Z2, Z3, Z4, and we just have to give the answer in the disk. And he gave a formula. Now this formula, I wrote it here, but it's not really explicit. It involves a hypergeometric function. So if you look in your table of hypergeometric functions or online, you will find this formula. It's known in great detail as power series. And he wrote a differential equation whose solution was this function. Now, we mathematicians, this was back in the 80s and 90s. I remember I was a postdoc in 91 when this conjecture became famous. My mentor, Peter Jones, asked me to check this with an undergrad. We did simulations. The undergrad, John Mattingly, is now a famous mathematician in his own right. But at the time he was an undergrad at Yale. He was good at simulation. So we checked the conformal invariance hypothesis, as did many other people in many other places. It seemed to work well in simulations, but no one could prove it. And this Cardy formula was remarkable. It seemed to be match experiments, but we couldn't even start to prove such a formula. And Cardy gave a reason, but not a proof. So this was stuck for a while, until a famous analyst entered the fray. This is Leonard Carlson, who is most famous for his proof that Fourier series of continuous functions converge almost everywhere. But he was interested in this probabilistic question, but being a great expert in complex analysis, he recognized that this function arises as a Schwarz-Christoffel transformation that maps the disk to a triangle, so that this very complicated looking function will become simple if you ask the question in a triangle. So what he showed is that if you believe conformal invariance, then Cardy's formula is equivalent to the following simple thing. So look at the triangle. So this is a 1 by 1 by 1 regular triangle. And mark on the right edge, you mark an interval of length x connected to the top, as you see in that picture. And now you do a percolation with a fine mesh inside the triangle. And you ask, what's the chance that the bottom side of length 1 will connect to this interval in the top of length x? And Carlson, just because he knew all these transformations by heart, he could recognize that Cardy's formula, together with conformal invariance, it would mean that in this triangle, this probability in the limit as the mesh goes to 0, it just goes to x. So now we as probabilists were much happier because there's maybe some hope in proving this thing in the triangle at least, because this is something, a statement we can understand. And if you look, for instance, at x equals a half, the truth of this becomes obvious by duality argument. So for x equals a half, it's true. So we already had a hold, but still, it took a while before this was proved. But Smirnov, Stanislav Smirnov, who was a earlier young mathematician who worked with Carlson, he recognized that Carlson's observation means that you should really attack this problem first, not on the square lattice, but on the hexagonal lattice, which, where the faces are hexagons and, and the edges are triangles. And so, the edges have degree 3. And he managed, so there's a hexagonal and triangular lattice, they are dual to each other. Anyway, he managed to prove this on the triangular lattice, that the probability indeed goes to x, and his proof also yielded the conformal invariance in the triangular lattice. So if you work with the triangular lattice with a small mesh, let the mesh go to 0, then Cardy's formula holds both in the original Cardy form and in the Carlson form, and conformal invariance holds. So he proved this in 2001, but initially he released, his paper was so short, it was 4 pages. And for me and for other experts, we understood from his paper that he solved the problem. But in 2006, the Fields Medal Committee didn't want to give him the Fields Medal because they said, well, experts say he's proved it, but he hasn't supplied the details. So he was eventually convinced to supply the details, and in 2010 he got the well-deserved Fields Medal for this amazing breakthrough. So another model that comes from statistical physics and turns out to be important is the Ising model. Because I'm running out of time, I won't be able to tell you much about that. Again, I'm going wrong with this, but in the Ising model, it's a model of magnetism where spins can be up and down, and again, there's a parameter like probability in percolation, there is temperature in the Ising model, and like in percolation, there are interfaces that separate different spins, and again, there's a whole collection of math physicists who advanced the study of this, starting with Lenz and Ising, and including Doobrushin, Kotetsky, and Schlossmann. I won't be able to do justice to their work now, so I'll have to just say 2 words, which is, in the Ising model, there is also a critical temperature where the model goes from multiple Gibbs states to a single Gibbs state. And the most interesting is the behavior at the critical temperature. And again, if you work in 2 dimensions, the interfaces that separate different spins turn out to be conformally invariant. And so there is a parallel with this percolation theory that was understood later. Okay. I told you about Ito and his stochastic calculus, and that led to SPDE. That grew into a big field, and one of the star practitioners of that field is Martin Heirer, who received the Field Medal in 2014. Again, he impacted, his work is related to the Navier-Stokes equation, to the KPZ equation. So it's a fantastic field, and again, because I'm surveying for you a whole century of probability, I just, I'm telling you about it without telling you any details. Another person important in our story is Greg Lawler, who introduced a key object, which is the loop-erased walk. So in 2 dimensions, I can look at a random walk, and the random walk will keep intersecting itself, and the object Lawler introduced is obtained when we take the walk, and every time it closes a loop, closes a cycle, we erase that loop. So we get a simple path without connections. And we can do this in any graph, but in 2 dimensions, we have to be careful because the walk is recurrent, so we will keep erasing. So the trick is to define the loop erased walk. We stop the walk when it reaches some large circle. So we start at the origin, we create a random walk, and when we reach the boundary of some big domain, we stop. Every time along the way, we erase the loops. And this object will be important in our story later, which we're getting to towards the end. But in particular, one result he got together with Wiener and Schramm that will appear shortly after is a mystery which physicists were interested in, predicted. Take 2 random walks in 2 dimensions and ask what is the chance that the 2 walks will stay disjoint for a long time. So this is beyond classical methods, and the answer is n to the minus 5/8, as it turns out. But this was only proved later when Lawler teamed up with Schramm and Wiener, but he was really setting the foundations of this topic back from his thesis in the 80s and an important book in 91. And for all his work, he received the Wolf Prize in 2019. And here are some pictures from the birthday party of Chris Birdsey, another important probabilist. And you see him cutting the cake. And just, I'm next to him in this photo. This is 2017 in Banff. There is Martin Heirer on the top left. And Lawler is on the right. It's hard to see him, but you can see him better on the bottom. So that's from 2017 birthday party. Some of you may recognize some more people there. I'll finish by quickly just telling you about the Loeve Prize. So Loeve Prize is a prize in probability theory given to influential probabilists under age 45. It started in 93 and the latest was in 2023. So I'm going to zoom through in the last 18 minutes these prize winners, and each one can write a whole book on their work. But the first one was David Aldous, and among his achievement, he proved the conjecture of the physicist Parisi. And Parisi just last year got a Nobel Prize for his work in physics, which was making remarkable, correct, not rigorous, but correct predictions, which were later proved based on his kind of physics methods. And he was so influential that he got a Nobel Prize. One of his predictions was about the assignment problem. It's written there, but I don't have time to go into details. And David Aldous actually proved one of those predictions back in 2001. He also did foundational work on mixing times of Markov chains, one of my favorite topics. So I wrote a book on it. But the pioneers of that topic are Aldous and Percy Diaconis. Here's a picture of Percy Diaconis holding one of my other books, my game theory book. But Percy and Aldous were the pioneers of understanding the topic of how fast does a Markov chain mix. And the key was to think that as you drive time forward, you also look at larger and larger chains. So before them, people were mostly looking, well, I have a Markov chain on a fixed number of states, I drive time to infinity, and everything is determined by eigenvalues. But they saw that the right way to think of the problem is, if I'm willing to run for more time, I should also consider larger and larger chains. And this is a whole topic, mixing time. I taught a course on it in BIMSA a couple of years ago. I'll do that again. But again, just a hint on this topic, which is important both in statistics, in statistical physics, in combinatorics, in computer science, randomized algorithms, and Aldous and Diaconis are really the key people there. Now we jump to the second Loeve Prize winner, which is Michel Talagrand, who just this year received the Abel Prize. And again, he proved another Parisi conjecture on spin glasses. He solved the long-standing problem that's about the maximum of a Gaussian process. You have a collection of normal or Gaussian random variables. They're not independent. We want to understand, given the correlation structure, what the maximum is. Many great mathematicians tried their hand at this problem, Dudley, Fernic, and the final answer was found by Talagrand. And again, he proved the most revolutionary concentration inequalities, again, a topic that was started with Paul Levy, continued with Vitaly Milman and others, and Talagrand proved what are considered the most important of those. The next one is Jean-François Le Gall, who took the study of fine properties of Brownian motion to really an ultimate level, and in terms of fractal properties, Hausdorff measure. He also constructed an important object called the Brownian snake. So if you look at random walk, it converges to a Brownian motion. So a Brownian motion is a path that keeps moving forward, and it's important in solving linear differential equations like the Laplacian. The Brownian snake is an object which moves forward and backward. So when it moves forward, it moves just like a Brownian motion. When it moves backward, it just erases part of its path. But it constantly moves forward, backward, backward, infinitesimal movement. And this turns out to be crucial in solving some nonlinear differential equations, as Le Gall understood and expounded. He also plays a key role in the most modern development, convergence of random maps to what's called a Brownian surface or Brownian map. I can't go into that, and he got the Wolf Prize in 2019. Next Loeb Prize recipient was Alain Sol Schnittmann, who got it in '99, and again refined works on random walks. I'll just tell you one of them. So you look at percolation cluster. I was personally interested in that question, and I worked on it with Berger and Gantert, but the ultimate result was obtained by Schnittmann. So you have a percolation cluster and you do a random walk on the cluster. Let's say that the cluster is infinite, but we do a biased walk. So it's not equally likely to go all directions. It goes with some higher weight to, say, to the right. So such a walk we expect to move at positive speed. But the amazing thing is that there's a non-monotonicity. The stronger the bias, the speed could, if the bias is very strong, the speed could be zero because the random walk gets stuck in traps and it takes it a long time to get out. If the bias is small enough, then the speed is positive. So this was a topic of debate between physicists, and they weren't even sure. Berger, Gantert, and I did it in 2 dimensions. And at the same time, independently, Schnittmann did the full result in all dimensions, which is much harder. Why is this erased? Well, that's me, so why does this keep going black? So I'll just mention that I'm a student of Hillel Furstenberg, who you saw before, and I will skip this slide because we have many slides to go. This is a photo from the birthday party of Gerard Ben Arous, his 60th birthday party in 2017, where many of these people appear. This is Terry Lyons, Ledoux, another important probabilist. Here is Schnittmann, Le Gall, Percy Diaconis. And why is this keep turning black? Anyway, it goes back, so it's okay. This is 2017. This is a picture with Schnittmann, again from the same 2017. This is Oded Schramm, who together with Smirnov got the most kind of revolutionary results in probability in the turn of the century. And one corollary of his work is a solution of a conjecture of Mandelbrot about the outer boundary of Brownian motion, which says that planar Brownian motion, if you run it for a finite time, then the outer boundary, which means the boundary of the unbounded domain in the complement of the motion, the outer boundary will have Hausdorff dimension 4/3. So Mandelbrot had a strange reason to conjecture this because there was another conjecture on self-avoiding walk, and he looked at the pictures and they looked similar, but this conjecture was proved used by Lawler, Schramm, and Werner using earlier work of Lawler, Werner, but dramatically new object which Schramm invented, which is the stochastic Loewe evolution. Why is this turning black all the time? Does anyone know? Something is not well attached. Okay, so the Schramm-Loewe evolution is a probabilistic version of a complex analysis innovation by Loewe, a way to describe a sequence of Riemann mappings. This is a beautiful but sophisticated concept, and since I just have 9 minutes, I'm going to point you to this Wikipedia page, but to find out more about the Schramm-Loewe evolution. When Schramm invented it, he called it stochastic Loewe evolution, and later people renamed it in his honor. Oded Schramm died in a tragic hiking accident in 2008, September 2008. But his influence is great on all of modern probability. I should say that, I'm again moving too fast, I should say that his invention was motivated by earlier work he did both on circle packings and some work he did joint with Beniamini, Lyons, and myself on uniform spanning trees. So I'll tell you just one thing about the uniform spanning tree that is relevant here. Suppose you take a finite graph, so n-vertex graph, and you take a uniform spanning tree. So you take a subtree of the graph that reaches all vertices, and you pick one uniformly. And then you can ask, so I have a uniform spanning tree in a graph, and you can ask, what is the connection between two nodes in the graph? So I have some graph, and I pick a uniform spanning tree. So this may be a uniform spanning tree. And now I pick two vertices, V and W, and I look at the path connecting V to W in the graph. So because I picked a random spanning tree, this path is itself random. Amazingly, as discovered by Robin P. Mantel, this random path exactly has a distribution of a loop-erased walk that starts at V and stops at W. So this connection between random spanning trees and loop-erased random walk is fundamental, and it was a basis of an algorithm called Wilson's algorithm developed by David Wilson, and was one of the motivations for Oded to define the SLE. Again, Wendelin Werner already appeared in this story for this joint work with Lawler and Schramm, the 4/3 dimension, but he also is a co-inventor of an important object, the Brownian loop soup, where you have lots of Brownian loops that have that are based at points of a Poisson process. And again, primarily for his work with Schramm and Lawler, he received the Field Medal in 2016, but earlier he got the Loeve Prize, which is why he's in this list. Then we move to Rick Kenyon. Again, Rick was a student of Thurston, just like Oded Schramm, so you see an influx in probability for people coming from topology, and he has a whole lot of important works. Even when Rick and I were both students, we wrote one Invenciones paper on intersections of Cantor sets. But Rick's most influential work is on dimers, which are like domino tilings, and on loop-erased walk. So particularly he proved that loop-erased walk takes time n to the 5/4 to reach distance n. So it kind of gives you that it's, if you want, its fractal dimension is 5/4. And this result was another key influence on Oded Schramm when he developed the SLE. Again, I can't give you the details of that here, but that was an important result in Acta Mathematica, appeared in 2000. Alice Guinet worked on random matrices, but these are different from the, so we have 5 more minutes. These are different from the matrices that Furstenberg and Kesten worked on. Furstenberg and Kesten took small random matrices, a fixed dimension, and multiplied them. Alice Guionet is part of a long stream of research starting from physics, where we look at large random matrices. So we don't multiply them, we try to understand their eigenvalues. And this is an enormous field with deep connections to nuclear physics, statistics, many contributors. Alice had a dramatic contribution here where she found how to apply Ito's stochastic calculus to solve problems in this area, a connection that didn't exist before. And she did this with multiple co-authors, some of them listed here, but she's really the originator of this fantastic connection, and for that she got the Loeve Prize. The next one is Scott Sheffield. I had the privilege of being the postdoc mentor of Scott Sheffield for a short time, but he was really the student of Amir Dembo. But I think all of us will say we learned more from Scott than he could ever learn from us. So Scott is was really a remarkable probabilist. In particular, I remember the day I was sitting with Oded Schramm and Rick Kenyon in Microsoft Research. We were chatting, and Scott Sheffield was a postdoc at the time. He burst into the room and said, the level lines of the Gaussian free field are SLE4. And this discovery of his took a paper of 100 pages that he wrote with Oded Schramm to really prove, but he had the insight that led to this. So Scott was in the last ICBS in BIMSA in last year. He gave a lecture which was crammed with results, crammed with people. Here are some slides from there. So the Gaussian free field is something you see there on the right. So it's the right analog of Brownian motion in higher dimensions. So, is the Gaussian free field, and it's a random surface, but you have to understand it as a distribution. And he understood that the level lines of it, which the definition is delicate, will be SLE4, and that connection was the foundation of a lot of modern research. Here's a picture from ICBS with Scott and a Japanese mathematician, Kumagai, who's an expert on Brownian motion on fractals. This is Shurav Chatterjee, a mathematician who graduated from Stanford. His advisor was Percy Diaconis, and he's now back at Stanford. So as you can see, I've written one Annals math paper with him, but his most famous contributions are related to Stein's method and concentration inequalities. I won't tell you more due to time, but he will be here, I am told, in the next ICBS. So don't miss his talk. Alexei Borodin combines ideas from representation theory and probability, and he got the Loeve Prize for that. Again, here are some references, but I have to move on. Then we have Hugo Dominel-Copin. He was briefly here in the last ICBS. Again, dramatic results on a host of areas in percolation, Ising model. In particular, the problem which is open for the percolation is the transition continuous in 3 dimensions. He, together with Eisenman and Sidorovicius, solved it for the Ising model. So this, I expected this would take decades, and he just did it a few years ago. So he received both the Loeve Prize and later the Fields Medal. He's a student of Stanislav Smirnov that we saw before. Alan Sly is a professor in Princeton, one of the most, again, amazing probabilists I ever met. And of his works, I'll mention one with Jian Ding, with arises from computer scientists, Jian Ding and Nike-san, Annals of Math, and also his work with Eyal Lubetsky that appeared in Invenciones Math, where they actually prove a conjecture that I made on cutoff for the Ising model, but it was much easier to make the conjecture than to prove it. So this is just some of his work, and his advisor Elchanan Mossel was actually my first student. So I'm very proud that he's my academic grandson. Ivan Corwin is the one before last in this story. Ivan Corwin got the Loeve Prize in 21 for the Kardar-Parishi-Zhang universality class. Again, it's a kind of analog of the central limit theorem. I'm about to finish this. It's an analog of the central limit theorem for a whole collection of more complex processes like eigenvalues of random matrices, and many mathematicians work on that, but Ivan has had some of the most dramatic results. And you can see a survey he wrote in the notices of the AMS 2016 describes his area beautifully, so I refer you to that. Don't have time for it. And the last Loeve Prize winner is my own student Jian Ding, who's now a professor in PKU. And his productivity and depth are just incredible. I already mentioned his work with Alan Sly and Nike-san. Here are a few of his works, of his dramatic works that keep appearing in the best journals. So again, I refer you to his website for more details, and I'm out of time. So the last slide, I'll mention my collaborations with Jian. So the first two were when he was, these are just some, we have like 11 papers together, but three of them are here. One is his first paper on cutoff, again, solving a question of Diaconis on cutoff. That was Jian's first paper. One is an annal math paper on relating cover time for random walk to Talagrand's theory of maximum of Gaussian processes. So again, I remember when I thought this would be true, I told Jian, you know, we hit a gold mine, but actually it took a lot of hard work on the part of Jian and our other collaborator, James Lee, to actually make this vision a reality. And that appeared in Annal Math in 2012. And finally, there's a work that's motivated by machine learning called Bandits with Switching Costs. I can't tell you more about it, but it's one of my all-time favorites. And this is the very last slide. So these are not Loeve Prize winners, but probably future Loeve Prize winners. So I'm happy to report that two of the best world experts on SLE and the best young probabilists are now working in Beijing, and that's Chin Sun in PKU and Hao Wu at Tsinghua. So that's a good point to finish. Thanks for your attention. Thank you. Clapping for myself.
Any questions? I want to know.
Can you speak louder? I can't.
I want to know how population model is related to physics, like the conformal property. How can we find that?
So in a way, percolation, so I'll have to be brief because because it's late, but percolation is the simplest statistical physics model, which actually was created by the mathematicians, but then adopted by physicists. And really the models physicists care about the most are maybe more involved models like the Ising model, and even more sophisticated ones, but it turns out that they all share similar features. And so when we understand percolation, that understanding is often the basis for understanding the other processes. And again, when mathematicians invented percolation, Hammersley and Welsh, they weren't focused on the critical value. They studied percolation at other values, but after the intervention of physics, that everyone understood, well, the critical value is where it's at, where the most interesting phenomena happen, and the Ising model has its own critical value, and behavior at criticality seems to be the same for a whole collection of models. I mean, criticality is something you encounter at home when you boil water, right? So when it transitions between two states of matter, that's kind of a critical temperature. And boiling water is a process that's mathematically a lot more complicated than percolation, but percolation is still complex, but simple enough that we can really understand it and then transfer that understanding successfully to other topics. And indeed, the work of Schramm on SLE that was initially crafted for loop erased walk and percolation turned out to later be a perfect fit to also describe interfaces of the Ising model and Potts model, other statistical physics models in 2 dimensions.
Any more questions? Okay, Professor Peres now working at BIMSA. So if you want to study probability, then please go to Professor.
I should emphasize that I work at BIMSA. So that's my research home, but I'm teaching here. So right now I'm teaching 3 classes, one on mathematical communication, how to give good lectures. I hope I did well this time. One is on opinion dynamics, how opinions in a graph change when individuals change their opinion based on their neighbors, and one which is topics in probability, so exactly random walks, percolation, and how these interact. And next semester I'll teach a course on ergodic theory and something else, and I look forward to see you there. And those who want to work in probability, do a thesis in probability, well, there's Professor Chenlin Gu sitting there with his blue mask. There's me, there's Hao Wu, Jianping Jian, Fan Yang. So there's a crew of probabilists here, all looking forward to work with you.
Now let's send Professor Peres.